let's, there's number 2. So the question is this a periodic function? It's sort of a, and of course, they can't show you the whole function, or maybe this is the whole function, you know, but they can't show it if it goes off to infinity. You just have to assume, you know, for example here, you can just assume this goes off to infinity. But the question is, does this fit the definition of a periodic function? And this is a place where it's good to go back to that formal definition, which is a periodic function is a function where f of x plus p is equal to f of x for all x in the domain. Now, while this, while this does kind of squiggle back and forth, you can see if I take some place here, say this spot, right? You can see that if you go what looks like a period, but it's not, to here, it's not the same value. So this is not a periodic function, period. Okay? So that was number 2, right? Number 8 is a little different. Okay, so 8, we look down here. Here we start at 60, and we have an A, 70 a B, 80 a C, 90 an F, 100 an R, 110 an F, 120 a C, 130 a B, 140 an A. So it took us, how much? It took us 80 to get to A. Well, that could be the period, right? 80 could be the period. Let's check. 70 plus 80, 150, yes, B. 80 plus 80, 160 is C. So as far as we can tell, you know, there's limited data here. This might not be a periodic function, but from what we can tell, it does fit that given that period. Now you want to be careful. You can see there's a C here and a C here. They're separated by 60 and then 40. So you might, you might jump to the conclusion, hey, C appears here and here, but it's not the same difference. So it's not a period. But a function, a periodic function, it could have, the same value for a large portion, right?
Even the C's are periodic. The C's.
I don't think so. I mean, they differ by. I mean, it comes up more than once, but that's just from 80 to 120 is 60, right? But from 20 to 160 is now 40.
Isn't 80 to 120 40?
I'm sorry?
80 to 120 is 40 units.
80 to 120 is 60.
80 plus 20
Oh, 40.
is
It is 40. I'm sorry. My brain isn't working. Okay. Yes. It is true that you're right. How did I miscalculate that? Having brain damage, I guess, from my youth. But that's not the period. It's not 40. The period is.
60. Wouldn't it be the longer?
Well, the problem is, that's just one value that happens to repeat. I mean, it would be easy to create a function where, I don't know, let's call it 100, right? Where it repeats this like this, right? The function's going to go through each of these points, right? But it might go through here like this, and then like this, and then like this. So, and then, you know, it's going to repeat like this. So the period is from here to here, not from here to here. Does that make sense? I guess I didn't do that right. It's not from here to here. This is not the period of the function, right? Because, you know, over here, you know, you don't get the same value.
Wouldn't it take place at like the max and minimum value, the periodic function, so to speak? Because
Not necessarily. Okay, so we're talking about a very general periodic function now. We're going to talk about sines and cosines, which are much more predictable. And in the case of a sine or a cosine, you typically would look for the peaks. That's what you're thinking of?
yeah, I guess that's
Yeah.
like the reading I did.
Yeah. Okay, but again, we're dealing with the very general, you know, form of a periodic function. I mean, a periodic function could be very strange too. I mean, it doesn't have to be continuous. It could be, it could just occur at certain points, right? And, you know, it could be something like that. That would be a periodic function too. As long as, you know, the domain is, say, the integers, right? And this equation is correct for some value of p, then we have a periodic function. Okay, other questions on the homework?
Yes, 35. I'm good.
35.
Yes, 35.
Alternating current. So, let's take a look at this. By the way, I'll put up an answer key either tonight or tomorrow, so you'll be able to look at it. Okay, electricity used in American households, alternating current, 120 volts, 60 hertz. So it goes from negative 120 volts to positive 120 volts. Okay, assume at t equals 0, the voltage is 0. Right, sketch the voltage as a function of time for the first 0.1 seconds. Right. I guess I'll do this on the overhead. So, it, you know, this is t equals 0, and we want through 0.1 seconds. So it might be good to look at the, put this here. You're not going to be able to read it, so I'll read it. All right, first, 60 hertz. So what is the period, the amplitude, the midline of the graph you. So let's think about this. So if it's 60 cycles per second, right, what is its period? Okay, it's 60 cycles per second, so that's the frequency. So the period is the reciprocal, so it's 1/60th of a second. So because we have 0.1 seconds, we're going to want to have how many intervals here?
6.
6, okay. So 1/60th 60ths, 3, 4, 5. This should be over here. 6 60ths is a 10th, right? So each of these is going to be a period. In that period, it goes up and down. Up and down. I know I'm displaying my fabulous, artistic skills here in poor life. Right, so, in fact, we're going to talk about this more on Wednesday, but this actually is a sine wave. All right. So there we are. State the period. We did that. What is the amplitude? Well, the amplitude, 120 to minus 120, so the amplitude is 120.
Yeah.
Right? The amplitude is, if you remember, it's the max plus the min over 2. So 100.
0?
No, 120 minus 120 is 240.
But you're saying max
No,
plus min, which is gonna be 120
Yeah.
plus
Oh.
minus 120.
I'm sorry,
Yeah, this one's-
that's the middle line, sorry, minus, thank you.
Yeah.
Okay, so max minus min divided by 2. And the midline, of course, is right here at 0. Oh, explain the real world meaning of each. Real world. Okay, well, the real world meaning of 60 of a second is that the voltage goes up and down every 60th of a second. It goes up and down 60 times a second. Maybe they want a physics explanation. Do they want to know what?
It's AC, it's alternating current.
Right.
So when it goes below 0, then it's negative. And you're not going to get into all that.
This isn't physics class. Yes. I'm not going to attempt to explain what voltage actually is.
Well, the practical thing is if you grab it, it's going to throw your hand back. If
It's
direct-
going to hurt.
If it's direct current, you can't let go.
Well, no. What's going to happen in either case, you can just grab alternating current or direct current. What's going to matter is, are you grounded? See, if you're grounded, the potential is going to come through you. You're going to get current coming through you, and that's what's going to hurt.
What they say is that direct current is much more dangerous.
I know that's true.
I think that's
There's a
one of the-
whole history of that.
There was a story about Tesla.
Tesla versus
Edison.
Edison, that's right.
And,
Edison brought in direct current.
right.
Okay, so let's explain to everybody. So there's this thing called voltage, which is how power is transmitted over electrical lines. Edison wanted a system where you just had, I don't know what, I'll make something up, like 60 volts of DC current. It's 2 wires, and there's like a ground wire and some voltage. And they actually started wiring cities in America with this. In particular, anyone here from Oakland? Yeah, okay. So about 15 years ago, I was in Oakland at a friend's house in an old hotel, and the elevator wasn't working. And they had to bring some special guy in to fix it because it was an old DC elevator. And the power company still had to produce this back from the days of Edison. I guess we're talking about early part of the last century. On the other hand, AC, the voltage between the 2 wires goes up and down, and there are disadvantages too. You may notice that on all your your computers all want to run on DC power. So you have a little box. This end hooks up to the AC, and this end is DC. So, I mean, that's a disadvantage. There are other interesting things too, like there's a way to use AC current to reduce, I'm going to use the word loosely, friction, right? If you run DC through a wire, you get a lot of heat and you lose a lot of energy. That can happen with AC also, but if you ever like drive down the highway through California, you see these big overhead power lines, and they're very high frequency, very high power, very high voltage. And what happens is it's very strange. Oh, I really don't want to get into the physics of this, but actually the electrical fields that are moving are outside of the wire, and so they don't get any resistance from the wire. So, all right, that's way far afield of mathematics here right now. We're going to come back to AC at some point. We're going to look at something else with it. Okay, are there other questions on the homework? Okay. All right, I want to digress for a minute. I want to talk about something that's very practical nature for this class. I want to talk about what an exact answer is versus an inexact answer. And my right hand doesn't spell very well. Exact. So the reason this is practical is you're going to have a quiz, and on the quiz I might have a problem where I say something like, just make up something. I have a circle and it has a radius of 2 and I want the circumference. And I say I want an exact answer. All right. So some of you may be tempted to say, well, 2 pi r, that's 2 pi times 2 pi, and then pull out your calculator and you go, okay, 4 pi is 12.6. Okay, that's not an exact answer, right? There's nothing wrong with just giving me this. Or another example is, what if the answer comes out to be this? Right? You put it into your calculator. Right? That's not an exact answer. In general, with exact answers, it's better to stay away from decimals. Sometimes a decimal will work, but you see, we have an error here. Those of you who are, more experienced with this stuff, you might have come across this. Anyone know what that means?
It means that the 3 continues to go on.
Yeah, it goes on to infinity, so this is an exact answer, but no reason to change this. So if I actually say I want an exact, I try and do this when I actually want one, I try and say it. If I don't say it, there are problems where it kind of begs for an exact answer. I can't complain if you don't. Inexact, you have a choice. You could leave it exact if you wanted. I mean, if your answer comes out to be 2.756 divided by 8.321, and you just want to leave it that way, okay. I can't complain. If you put it through a calculator, okay, there's a whole science of, well, how many decimals should this have, right? 756 divided by 0.21. So you notice we get a very long decimal number here. Those of you involved with science will find that it's not really correct to say that this is 331210, whatever. Because now you're ascribing more accuracy to this number than either of these numbers. And we're not going to get into that. I'm not going to worry about this. It's not part of the curriculum. You should just know that this will be fine, or maybe one more number. If I want a certain number of decimals or a certain number of numbers in the answer, I will state it. If I don't state it, that's fine. Whatever you come up with is probably okay. Okay, are there any questions about this? Because this is often an area of confusion to students at this level. No? Everybody happy with this? Okay. All right. So we're going to move on to today's subject, which I have up there. We're going to talk about trigonometric functions, actually just the sine and cosine today, and something called a unit circle. All right, so if you've run into this before, you've probably run into this kind of standard way of thinking about the sine and cosine. Is you have a right triangle, you have an angle, and the right triangle has the longer side, of course, opposite the right angle is called the hypotenuse. The side across from the angle is called the opposite, and the side, on the base here is called the adjacent to the angle. And we then define functions, sine, cosine. I'm going to leave tangents in here for the moment. The sine is the opposite over the hypotenuse, O over H. The cosine is defined as the adjacent over H, and the tangent, which is the sine over the cosine, is the opposite over the adjacent. Since I went to school, it seems to be traditional to use this memory device. You have to remember SOHCAHTOA. Has anyone run into this before? Okay, all right. Anyone who hasn't run into it? Okay. So it's just a way of remembering it. If you can remember so, ha, wa. So what this means is the sine is the opposite over the hypotenuse. The cosine is the adjacent over the hypotenuse. And the tangent is the opposite over the adjacent. It's just a way to remember which is which. Now, I want you to note this only works for angles between 0 and 90 degrees, or pi over 2. If you have 0 degrees, it's not a triangle. If you have 90 degrees, you don't have a triangle either, right? So we want to extend this. We want to extend these functions so that their domain is any value, any theta you can come up with. Okay, before I do that, I'd like some feedback not now, but I'd love to
Excuse
have
me?
feedback on these little videos I've come up with.
Excuse me? Can you show the last page, please?
Oh,
Or just keep it under camera?
well, I'm gonna switch over to my laptop, so I'll put it back when I'm done, all right?
Okay.
Let's see. There it is. I hate the music. Why? But I took off the music, and you wouldn't hear what the guy has to say. So, this is just a little review of what we just did.
Suppose we call this angle T. If we expand or contract the triangle by a scaling factor, we change the sides, but we don't change the angle T. Or the two internal ratios. Or B over C. Now we will show that the ratio A over C is equal to the sine of T, and the ratio B over C is the cosine of T. Scale a triangle by the particular scaling factor 1 over C. This gives a triangle with a hypotenuse of length 1. Use this as the radius of the circle. Then T is the radian measure of this angle. This point has a vertical coordinate sine T and a horizontal coordinate cosine T. But these are just the lengths of the other two sides of the triangle. This shows that sines and cosines are ratios of lengths of sides of a right triangle. If the right triangle is oriented differently, it's easy to remember the ratios by thinking of them this way. The sine of this angle is the length of the side opposite the angle divided by the length of the hypotenuse. And the cosine of the angle is the length of the side adjacent to the angle divided by the length of the hypotenuse.
All right, so we're going to just talk for a minute about what you could do with this definition. What kind of problems can we solve with this? Well, if we have a triangle and we have three components of that triangle, other than three angles, then that triangle is completely determined. Does anyone know why if you have all three angles, that really doesn't determine the triangle? You can have two different triangles with the same angles. Anyone recall what we call that?
Isosceles?
That would be if two sides are the same. I'm saying two triangles.
Oh, similar? Similar, congruent.
Similar, yes. You can have similar triangles that are different, but they have all the same angles. So as long as you have at least one side, that determines a triangle. Now let's take a look at this problem. We know two angles. We have a 60-degree angle, and we have a right angle, and we know the hypotenuse is 10. So the question is, how would we find the other components? Well, one of the components is really easy. What would be the third angle in this triangle? 30, that's right. Because the sum of the angles has to be 180. All right, at this point, we're going to look at our trig functions, and we're going to say, okay, what's the sine of 60 degrees? Well, it's going to turn out to be the square root of 3 over 2, and the cosine is going to be a half. So that's going to enable us to figure out what these other sides are. Because we know the opposite over the hypotenuse, that is the sine of 60 degrees. And that's equal to the square of 3 over 2. Well, we know the hypotenuse, that's 10. So it's just this opposite here. I guess I'm going to change that to x. And now I can just solve for x. X is just 10 square root of 3 over 2. At this point, I could use the cosine to find the adjacent side, or there's one other way I could find the adjacent side. Anyone know the alternative way to find the adjacent side? If I have two sides of a, yes?
But finding the sine of 30, it's the same thing.
That's, yes, you're correct. You could do that. You could kind of turn the triangle this way, right? But I'm actually thinking of a
I just realized what you meant. But Pythagorean theory.
Pythagorean theorem. Thank you. Very
Sorry.
good. Yeah. You know that the square of this side plus the square of this side equals the square of 10. Okay. Here's a little different problem. How can we find the missing angles? Well, here we have we have the adjacent side 4 and the hypotenuse 10. So 4 over 10, that's the adjacent over the hypotenuse, that's what? That's the cosine of theta. Well, for now, you can go back to your calculator, right, and enter 10, that's no surprise. Before we find the inverse function here, we're going to find the inverse cosine. We want to check something. If you don't have a TI calculator, I don't know how you do this on your calculator. But on a TI calculator, you're going to hit the mode button, and you're going to look down here and see radian versus degree. And that's going to determine both what your input to your trig functions, your sines and cosines is, but it's also going to determine your output from the inverse function. Right? So I think for now let's use degrees. And I'm going to say, okay, what's the inverse cosine? That's the second button plus the cosine button of 0.4. And the answer is 66. We're just going to say 66 degrees right now. All right. So at this point, we have one angle. We have the right angle. We can find the third angle. And then we're in the same place we were on the other problem. We can use the sine and cosine of 60. We can use either the sine or cosine of 66 degrees to find the missing side. Okay, this is how you might have learned about sines and cosines. Are there any questions so far? Okay.
Actually, did you go back over the calculator real quick, like where I go to change it?
Okay, so you see here there's a mode button. The close in on that. You hit mode, and then you use the cursor to move around. There are various things that, you know, we'll become familiar with more and more of these, you know, as we play around with them. But you just put it over whichever you want to choose, and then you hit enter. Right, so now it's in radian mode. To get out of this, you want to do quit, which is second mode button. And let's try it again in this mode. Inverse cosine of 0.4. So now it says 1.159 radians.
How do you do inverse cosine?
Okay, take a look on the calculator, see the blue labels? Like on the buttons, there's a white or a black label.
Yeah, I see.
So there are these blue labels, and those blue labels you get by, if you press the second key, you see it's like a shift key on a keyboard, and you see the little blink here, and,
All right, yeah, I understand, I just wanted to know exactly what it was, I get it.
okay, good. All right. And just so you know, if somebody asks a question, and it's a simple question, sometimes I'll embellish it, not because I don't think you don't know, but because I want to make sure the whole class knows. Okay? All right, we're gonna go back in time a little, have a little history lesson. When I was in high school, actually when I was in a senior in high school, a company called Hewlett-Packard, heard of it, came up with the first handheld scientific calculator. It was about this big. Well, I guess it was actually a little smaller than this. It cost $400. $400 or $600. Anyway, it was very expensive. It used a weird system called RPN, reverse Polish notation. I say weird, most people think it's weird. If you're a computer programmer, you probably are a little more familiar with it. But before then, you know, how did we do calculations? Well, we had books with tables. And this is just an example. I guess I could zoom out to show you. This is one page, and you can see here we have the table for 28 degrees and 29 degrees. So you can figure this is, you know, many pages. And the way you look up an angle is you go to the page where the angle is, and then down here you have the minutes. Right? So it goes all the way from 0 to 60 minutes. And then we have, you know, you can look up the sine, cosine, tangent, and various other functions. This is to 5 decimal places. Now your calculators can easily give you, I don't know, 10, 12 digits. But this is what you're limited to. If you wanted sine or cosine to more places, you know, you're talking about a very thick volume. Now, I'm just going to mention one other thing because I think it's fun. In Santa Clara, there's a museum called the Computer Museum? Museum of Computers?
Where?
It's in Mountain
Mountain View, okay.
In Google Plex.
Yeah, if you get a chance, you know, it's a fun place to look through stuff. And I don't know if they still have it there, but for a while they had a machine called the Babbage difference engine. It's a big, giant mechanical thing with a crank and settings, and it was designed by a mathematician named Babbage, who, and you know, he's related to Ada. If you're a computer programmer, you've heard of the Ada language, Ada Lovelace. Anyway, he designed this machine, and its purpose was to calculate tables like this. He figured out a way to do this mechanically. And the only thing is, he never had the technology to build it. And then a few years ago, some very wealthy founder of some, you know, either internet company or tech company paid to have them make 2 of them. So they may still have it over there. Anyway, it used to be a big deal and difficult. Now we don't do this anymore, right? Okay, there's one more thing I want to point out, which came up a little earlier. if you look at a triangle, the right triangle with angle theta, you know that the opposite angle, not the right angle, but the other angle is 90 degrees minus theta. And you could take this triangle and you could just flip it over. You could kind of switch the angles this way. So let's take a look at that. What do we call these angles? They're complementary angles, right? Okay, so note that in this diagram that the sine is A over C and the cosine is B over C. Opposite over hypotenuse, adjacent over hypotenuse. But in this triangle, we have the cosine of 90 degrees minus theta, right? The adjacent, which is A over C over the hypotenuse, is also A over C. And the sine of the complementary angle, 90 minus theta, is B over C. So that tells us that the sine of 90 degrees minus theta is the cosine of theta, and the cosine of 90 degrees minus theta is the sine of theta. This is an equality that we call an identity, something we're going to study a little later in the class. Well, the upshot of this is you don't really need to know all the sines and cosines between 0 and 90. You only need to know, let's see, between 0 and 45. Because if, for example, you want to find, say, the sine of, say, 70 degrees, you know that's the cosine of 90 degrees minus 70 degrees. It's just the cosine of 20 degrees. So you can always kind of, squeeze that way. If you're stuck using a table. If you're using a calculator, you probably don't care. Which I guess is what we're probably going to be doing here. Okay. I'm just going to repeat this. Always check the mode. One of the most common errors I run into when people are doing tests and quizzes and homework, they give me an answer and it's the wrong answer, and I say, how did I come up with this crazy answer? And then I just switched the mode, and that's how they did it. All right. Okay. Let's see here. A little too early for the break. I'm gonna just stop for a minute, catch my breath before we zoom on. Are there any questions up till now, or? I get the feeling a lot of this is very familiar to people. Is that right? Okay. Probably had some of this, a lot of you had it in high school. Is it completely new to anyone? All right. All right, let's continue on. We're going to take a new view of the trig functions, and we're going to look at them in terms of a unit circle. That is, we draw a circle of radius 1, and we take a point on that circle, and the angle formed by drawing a radius to that point and the x-axis, that gives us some angle theta. And we define the sine and the cosine in terms of the coordinates of that point. The cosine is the x-coordinate, and the sine is the y-coordinate. Now, the little video we just showed demonstrated that that's really an equivalent definition to the opposite over adjacent, opposite over hypotenuse, adjacent over hypotenuse definition. So why is it we want to do this? Well, this way of viewing the sines and cosines now works for angles greater than 90 degrees. Right? In other words, wherever that point is, whatever its coordinates are, that's what we define a sine and cosine as. In this particular example, we have an obtuse angle, one greater than 90 degrees. And we can see here that we still have a value for sine and cosine, but what happens to the cosine, which is the x-coordinate? It's now negative. Now that doesn't make any sense for a right triangle, but that's fine. Now we're dealing with a function, and we're expanding its domain. So one thing to keep in mind is that in the first quadrant here, the sine and cosine are always positive. But here you see in the second quadrant, the cosine is now negative and the sine is positive.
Same as a Cartesian plane.
This is a Cartesian plane, yes. It's not a complex plane. Or could it be something else?
Oh no, I was just wondering if it was.
Yeah. Okay. In the third quadrant, you see both coordinates are negative, right? This is an angle between what? 180 and 270 degrees. And then finally we have, in the fourth quadrant, we have the cosine is now positive, but the sine is negative. Now, of course, I just started at the x-axis and went in a positive direction. But of course, you could go in a negative direction, right? So anywhere from 0 to minus 90 degrees is also here in the fourth quadrant. Okay. We're not quite done. Angles are not limited to 360 degrees or 2 pi either. You can have an angle that goes all the way around, and now it's back in the first quadrant. Or it can, as I mentioned before, it could be negative between 0 and 90, and now it's in the fourth quadrant. Okay, so here's kind of a map showing you the SIGN sign of each of these functions in each of the quadrants. There's a nice symmetry here, you know, positive, positive, negative, 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 positive, positive, negative. And you should try and familiarize yourself with this a little bit. It's helpful to kind of be oriented. Again, what you always want to do is take a look at the coordinate, knowing that the first coordinate is the cosine and the second is the sine, and then just look where you are on the xy axis, right? If you're on this side of the y-axis, then your cosine is negative. If you're on this side of the x-axis, your sine is negative, and likewise, above the x-axis, your sine is positive, and to the right of the y-axis, your cosine is going to be positive. Right. We also can define sines and cosines for some angles that, again, don't make sense, you know, in the context of a right triangle. So I guess I should Should have had a picture here. But if I look at 0, the angle 0, you can see that the cosine, the first coordinate is 1, right? And the second coordinate, the y-coordinate, is now 0. So we now have sine of 0 is 0, cosine of 0 is 1. We come up here 90 degrees. Now we're on the y-axis. The sine has now become 1, and the cosine has become 0. As we keep going around, the sine again becomes 0. 0 at 0 and 0 at 180. But the cosine is now minus 1, right? Because it's to the left of the y-axis. And again, we keep going to 70 degrees, and now we've kind of switched. The sine is now -1, and the cosine is 0. And if we keep going all the way back up to 360 degrees, then we're back with the sine 0 and the cosine 1 again. So we can keep going around this circle, and we get the same values repeating, which makes this a periodic function. Right? Okay.
Oh, yeah, use the.
I think it's a good time for a break. So, please come back to. Okay, we're going to talk about something now called a reference angle. A reference angle is an angle in the first quadrant. And every angle possible has a corresponding reference angle. When you look at an angle and you find its reference angle, the sines and cosines of the angle and the reference angle will be the same or the opposite of that angle. So to start with, we're gonna look at angles between 0 and 360 degrees. Now, if you have an angle that's between 0 and 90 degrees, it's already a reference angle, so it's its own reference angle, and it's not very interesting. Let's take a look at an angle in the second quadrant. Okay. So here we have an angle theta in the second quadrant, and what we do is we take a parallel line parallel to the x-axis and draw it through that point and see where it intersects the circle in the first quadrant. And that gives us our reference angle. I'm going to refer to these angles as theta and theta r being the reference angle. So you might want to note that this angle in the second quadrant, its reference angle is always just 180 minus theta. Right? Now, again, if you look here at the cosine and the sine, which are the coordinates.
Can you zoom out?
I'm sorry? The cosine and the sine of these angles, what's going to happen? Well, the y value, which is the sine, is going to be the same, but the cosine value is going to be the opposite. All right? So, again, what we have is sine of the reference angle is equal to the sine. but the cosine is equal to the opposite. The cosine of the reference angle is equal to the opposite of the cosine of the angle. So that's a reference angle in the second quadrant. In the third quadrant, it's a little easier. We have again an angle here in the third quadrant. All you need to do in this case is to extend the ray in the opposite direction over here and see where it intersects in the first quadrant. And here it's a little simpler. The sines and cosines are just the opposite. They're the negative of the reference angle, for the reference angle. So in particular, sine of the reference angle is the opposite of the sine of the angle, and the cosine of the reference angle is the opposite of the cosine. Again, this is now for the third quadrant. And now we have a little symmetry here with the second quadrant, when we go to the fourth quadrant. Here we have an angle in the fourth quadrant. We draw a line parallel to the y-axis now, and that intersects again in the first quadrant, giving us our reference angle. Let me back up a second. I guess I should point this out. In the third quadrant, the reference angle is always theta minus 180 degrees. Going back to the fourth quadrant, the angle is now 360 minus the angle, the reference angle. And here we have the sine is now the opposite, but the cosine is the same. So the idea is, if you want to find the value of a sine or a cosine, and you don't know the angle outside of 0 to 90 degrees, you can still find it. You find the reference angle, you find its cosine and sine, and then you decide, is it the same value or the opposite value. So that covers all the angles between 0 and 360 degrees. But, yes.
Is this second quadrant or this fourth or something?
I'm sorry, say again.
It's like you're not that for the second quarter, right? But it's supposed to be fourth, right?
The note that you have under there, it says this is for second quadrant.
It's
Oh.
fourth, right?
Oh, that's because I copy and paste and forget. Thank you. That's a correction I'll put in the notes. Right. Thank you. Okay, so what do we do for the rest of the domain? Well, if you have an angle that's either less than 0 or greater than 360, then there's some angle, which I'm going to call theta sub u, for which this is true. For some n, some integer n, you can add n times 360 degrees to that angle and get the angle you're looking for. But with theta sub u between 0 and 360 degrees. So really all I'm saying is that circle. And you have some angle that may go around some number of times. But that angle is equivalent to some angle between 0 and 360 degrees, which has the same sines and cosines. Again, this being related to the fact that sines and cosines are periodic functions with a period of 360 degrees or 2 pi. So now we can, you know, I mean, if we were living back in the 60s, we have our table of sines and cosines. It just goes from 0 to 45 degrees, but we can find the sine and cosine of any angle. Okay, so where we are now is I want you to pass these around and work on the first page. Here we're going to try and find some reference angles for certain angles. They're going to have extras. Easy enough for everyone. Still waiting. Okay. Anyone?
No,
Okay. Okay, so the reference angle is the corresponding angle that's in the first quadrant. So, for example, if the angle's in the second quadrant, its reference angle you get by drawing a line this way. Now, in particular, it's in the second quadrant. You can find that angle out. It's 180 degrees minus the angle.
and that's minus the given angle that you have.
If that angle is in the second quadrant.
So the,
It's in the third quadrant,
it's 270.
you subtract the angle from 180.
Even in the third quadrant, it's not 270.
No.
Well,
I
you kind of blew through that. I didn't really
Yeah,
have time to write down.
Okay, so let's take a look here, right? So if this is theta, so let's say quadrant, right? In the first quadrant, the reference angle is theta. In the second quadrant, right, this is the angle, this is 180 degrees minus theta. In the third quadrant, over here, it's now theta minus 180 degrees. And in the fourth quadrant, I'm getting dyslexic here now.
I goes before the B.
Yeah. I know it goes before it, I'm just dyslexic, all right? So now I'm in the fourth quadrant, and 360 degrees minus the angle.
Or just,
If this is theta, and this is like minus theta, and 360 degrees minus theta is a coterminal angle. Is that right?
Yes.
No, that's not, wait a minute, wait a minute,
No.
wait a minute, hold on. Yeah,
Yeah, that's right.
yeah, that's right.
that's right.
That's right. If you didn't understand it, it's okay.
No, actually,
Okay. You look puzzled, that's all.
no, that's just thinking.
Yeah. So, probably the first thing, no, because the reference angle has to be between 0 and 90. But if an angle, if you have negative, if you have something in the fourth quadrant here that's just negative, right, between negative and 0 and 90, it's just going to be the opposite, right? In other words,
How does it work?
if I have an angle down here, right? So, let's say negative 25, right? So the reference angle is just going to be positive 25. But that's if it's in this quadrant. Now, if it was like negative, say it was negative 100 degrees. Right? So the reference angle is now over here. How do we figure that out? Well,
And then for negative 65.
the angle that goes around here is now 280 degrees, right? And then we subtract 180 from that. Oh, so it's 100 degrees. No, because that's not a reference angle. What am I doing wrong here? This is 100 degrees, negative 100 degrees. You add 360. So this is 280 degrees. My brain is, I can't figure it out. I'll think about that for a minute.
70 degrees is
Yeah,
So if I have an angle,
huh?
it's minus 180 degrees. Oh, I know. It's minus 100 degrees. So that's really,
I don't know how I got
260 degrees. And what did I say for this quadrant? We subtract 180.
7.
So
It's the same
I'm
angle?
not showing you what I'm doing here. So 260 minus 180 is 80 degrees.
Mm.
So it'll be
Yeah, yeah,
80 degree angle. Should I do that again, or did that make sense the second time?
Okay, then.
Okay.
А? Нет? Ну, если по-другому, или все? Вот, это тот же угол. Видишь? Это... How do you call this sign? Theta?
Theta?
Theta.
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 Okay,
Can we go over it very quickly? We'll go over it, right?
we're gonna go over it, yes. Is it too soon? Okay. Okay, so for number one, 70 degrees. What's
That's
the
same
reference
70?
angle?
The same 70 degrees?
It's 70 degrees, absolutely. Okay? Which quadrant is that in?
First.
The first. Okay. Number two, 150 degrees, that's in which quadrant?
Second quadrant.
And the reference angle is 30 degrees. Okay. Number three, 255 degrees.
Third quadrant.
Yeah. It's, again, just, I'm gonna write these out both in degrees and radians. Obviously, these are radians. Here we have, remember, 90 degrees or pi over 2. We have 180 degrees or pi. And down here, it's good to know this is 270 degrees or 3 pi over 2. Those are numbers you might want to let them seep in. Okay, so this is which quadrant? Third, right? It's less than 270, but it's greater than 180. And so its reference angle is
75.
75 degrees. Does that sound right?
Yes.
255 minus 180? Questions?
Would it be 255 minus 180, right?
It would be 255 minus 180. Is that 75?
Yep.
Okay. Right, number four, minus 65 degrees. Fourth quadrant. And its reference angle is 65 degrees.
No. 360 minus 65 will be 425.
Okay, these only work if the angle is between 0 and 360.
Okay.
You can always move the angle to between 0 and 360 by adding or subtracting 360 some number of times,
Okay.
right?
So I need to find.
That's the long, in this case, in the case of this one, that's the long way to do it. The easy way to do it is to just see, okay, if this is minus 65 in the fourth quadrant, the reference angle will just be 65. We'll just kind of flip it over.
Okay. Does that mean the reference angle is always positive?
The reference angle is always between 0 and 90 degrees.
And then,
So, yes, it is always
so to
positive.
go back to number 3, is it 75 degrees?
Yeah, 75.
I got 15 degrees. Because 255 would be in the third quadrant, so that'd be 270 degrees minus theta.
No, it would be
No,
theta minus
no.
180.
It's tempting,
Oh, okay.
it's
I
tempting
thought the same
to
thing.
think, you
I
know, right? But then this would be 0 minus theta, and it would be negative
Oh, right.
theta.
Yeah, okay.
There's something happening with that equation as you go back and forth. Yes?
May you like go over number 4, because I wouldn't have picked up that negative 61.
Okay.
These was in quadrant 4.
Okay, let's do it the hard way,
No.
right?
Can we do it the easy way?
No. We're gonna do it the hard way, then we're gonna do it the easy way. Okay. So the angle is negative 65. So we want to find a equivalent or coterminal angle that's between 0 and 360. So how do we do that? We have to add or subtract some multiple of 365. So we're just going to add 365.
365 or 360?
I'm sorry, 360. Right? So we add 360, which is when we subtract, and that's 295. So this is now coterminal with this angle, right? Minus 65 is down here, and 295 is here. So now we're going to use this formula. We're going to subtract our angle from 360. So 360 minus 295 is 65. So that's over here. Now, having done it the hard way, you can see right away that if this is negative 65 here, it's just going to be positive 65. I mean, this could get uglier. I could give you something like, say, negative 3,743 degrees. What's the reference angle? Well, okay, we can take out
That's
360,000, that's 143. Oh, I guess we want to add that, negative 143. So we want to add 360 to that. So that's going to be 217 degrees. And now 217 is going to be in the third quadrant, so I'll subtract 180 from that. So I probably won't do that to you. I mean, I suppose I could. Okay, well, we have a problem a little like that in number 5. The first thing we want to do here is get between 0 and 360 degrees. So if I subtract 360 here, 7, 2, now it's an angle of 127 degrees, which is in which quadrant? Second quadrant. Right? And so we're going to subtract that from 180, and we're going to get 53 degrees. Is this stuff okay?
Yes.
All right, let's now switch gears a little here. Same type of problems, except now we are looking at radians. Right? So for pi over 7, right? Where is that?
First quadrant.
In the first quadrant. Remember, first quadrant goes from 0 to pi over 2. So it's in the first quadrant, and its reference angle is itself, pi over 7. Okay, this next one, a little trickier. We have to, on our thinking caps here. What's 44 divided by 9?
4.
4 it's almost 5, right?
4, 8 over 9, 5.
So we want to take away 360, 720, which is 2 pi, 4 pi, right? So we want to subtract 4 pi from this.
Wait, I'm sorry. Can you
So-
go over that?
Hmm?
May you go over that one more time?
Oh, okay. 44 over 9 is between 4 and 5 pi.
Oh, okay, that's, okay. So we go 5.
44 divided by 9, 4, 36, 8, 8 ninths. Between 4 and 5 pi. So I'm going to subtract 4 pi, right? 2 pi and then 2 pi. So just going to take the pi's out here. 4 over 9 is 36. So this is 8 ninths pi. All right, simplified it a little bit. Now, 8 ninths pi is where? Second quadrant, right? It's almost pi, right? It's greater than pi over 2. All right. So in the second quadrant, I want to subtract this angle from 180, which is pi, right? So it's going to be pi minus 8 ninths pi, or pi over 9. Little different orientation here. Okay, let's look at the last one. Negative 24 over 10 pi. Okay. Negative 24 over 10 pi, that's between negative 2 pi and negative 3 pi. So I want to add some pi's back, right? How many pi's do I want to? It sounds like a bakery class. How many pi's do I want to add back here? Remember, it's a multiple of 2, right? So will 2 be enough to get it back into between 0 and 2 pi? You can always just try it, right? Let's just add 2 pi, so that's 20 over 10 pi. Well, that's negative 4 pi over 10. That wasn't enough. So let's add another 20 over 10 pi. So it's 16 over 10 pi, which is 4/5 pi. No. Yeah. No.
16 over 10.
8/5 pi. Okay, so 8/5 pi, it's greater than pi. Is it less than 3/2 pi? I think so. Let's see. Actually do some basic math here. 8/5. 8 divided by 5 is 1, 5, 3.6. It's 1.6 pi. And 3/2 pi is 1.5 pi. Oh, so it's in the fourth quadrant. Does that make sense? Okay, so it's in the fourth quadrant, so we're going to subtract it from 2 pi. So 2 pi minus 8/5 pi, well that's 10/5 pi minus 8/5 pi is 2/5 pi. So it's in the fourth quadrant, and its reference angle is 2/5 pi. This is a little tricky math. It's not, nothing earth-shattering yet. We're going to get to that. Okay, all right, onwards. Someone at the break asked me, how do I know that the sine of 60 is the square root of 3 over 2 and the cosine of 60 is 1/2? So what I want you all to do is listen very carefully, stop me at any point, just yell something out because I'm going to be staring at the paper. I'm going to show you how to, assuming you know your basic geometry, I'm going to show you how to figure this out. All right? What we're going to look at is some special angles whose sines and cosines have exact values. Right? Remember, when we're going to go on the quiz, if I say an exact value, you're going to need to either be able to figure these out or know them. You can memorize them, but I think this is a much better way to go about this. All right, so we're going to start with a very basic geometric shape, which is an equilateral triangle. We know that, and we're going to give this equilateral triangle, we could use any side if we want, but we're just going to say 1. Right? And we know the angles are, for an equilateral triangle, the angles are, they're all, how many degrees? 60? Okay. We now drop a perpendicular from the apex to the base, which bisects this triangle. It bisects the triangle into 2 triangles. Since it's perpendicular, this is a right angle, and since this is now a complementary angle to 60, this angle has to be 30. So we have a 30, 60, 90 triangle, and what we're going to pull out of this is the sines and cosines of 30 and 60 degrees. Now, we know that the side is 1, so the base here of this half triangle now has to be 1/2. You can do this. Think about this. This is all very straightforward. So now, the only thing we really need that we don't have, what's the height of this leg here? All right? What's the height of the triangle? Well, what are we going to use?
1/2 square.
What theorem? What famous theorem are we going to use? Pythagorean theorem. That tells us 1 squared minus 1/2 squared is going to be equal to, let's call this x squared, or x is the square root of 1 minus 1/4. So x is the square root of 3/4, and simplifying, x equals the square root of 3 over 2. I know it's too late for most of you, but this is really good numbers to have really in your head clearly for the SATs. I know it's too late. Right? We're in college already. Okay, good. All right, so now we want to let's find the sine of 60 degrees. Well, that's the opposite over the hypotenuse. That's square root of 3 over 2 over 1. It's square root of 3 over 2. Cosine of 60 degrees is now the adjacent over the hypotenuse, 1/2 over 1, or 1/2. So now we know the exact value of the sine and cosine of 60 degrees. But we also know the sine and cosine of 30 degrees, the complementary angle. Remember, if the sine of 60 degrees is square root of 3 over 2, then the cosine of 30 degrees will also be the square root of 3 over 2. And the sine, since the cosine of 60 degrees is 1/2, the sine of 30 degrees is 1/2. Very important, exact sine and cosine for a very specific angle. 30 and 60 degrees. Nobody stopped me. Is everybody comfortable with that? Okay. In my notes, you'll see I have a little diagram that looks almost the same where I don't explain it quite as well. You just have to go over it. Really good to have this something you could, you know, it won't be on a test. I won't say, show me this, but there'll be problems where you need an exact answer. And, you know, if you go to your calculator, right, what's going to happen? Say, oh, remember, always check. Nope, we're in radians. Let's do degrees. If I say, oh, that was a little closer. If I say the sine of 60 degrees, oh, what's that? How do we know? That's not an exact number. I don't care how many decimal points you put on there, it's not exactly it. Now, we could do this with the calculator. We could say, all right, let's check. Square root of 3 divided by 2. It looks like the same number, doesn't it?
Interesting.
Yeah. Actually, if I take that number I just created and subtract the sine of 60 degrees, the calculator is going to tell me it's 0. Well, that tells us something. Within the accuracy of the calculator, those numbers are the same. Okay. That was the hard exact value, right? This is the easy one. We again take a right triangle. We take an isosceles right triangle with legs that are 1. What are the angles?
45, 45, 90.
45, 90. And what's the hypotenuse? Square root of 2. Okay, so what is the sine of 45 degrees?
Square root of 2.
1, right? This is the
Yeah,
hypotenuse,
1
right?
over square.
1 over the square root of 2. What's the cosine of 45 degrees? You're making this hard on yourself. It's just 1 over the square root of 2. That identity actually kind of comes in kind of neat here. Because if you say, what's the sine of 45 degrees, it has to equal the cosine of 90 minus 45 degrees, right? So they have to be equal. It has to be the cosine of 45 degrees. Okay, very important exact values we can get for sine and cosine. Much later in the class, we're going to learn how you can extend that a little bit. There are other angles you can get exact values for using these as a starting point, but we're not going to get there for a while. Okay, if you turn your worksheet over, here's the worksheet. We have a table. Ooh. Okay. This is going to be a little tedious. You know, it's going to cause a little pain. But you know, like when you go to the gym, no pain, no gain, right? So here we have 1, 2, 3, 4, 16 angles. Once you get started, I suggest you do the first column, right? And then, how are we going to do the rest? Well, we're gonna find the reference angle, and we're gonna go from there. So we're not gonna have to do that much calculation, right? But I want exact answers here, right? I want the exact values. So why don't you work on that for maybe another 10 minutes? And if you get done with it early and you're bored, you can work on problem number 3. Yes?
In the first line, you have 180 twice. I think one of them should be 170.
Oh,
280.
oh,
Oh, 270.
you're quite correct. 240, yeah, that's more of me, fix this one. What should that be?
270?
270, I think you're right. Thank you. See, you got people here smarter than the teacher. That's a good sign. So it's gotta be 1. And again, you know, if you work with your neighbors on these, whatever you prefer. It's over here. Okay, thank you. I don't know why I remember that. No. He's 8. You're not 8. You're Jessica. Great. I don't know why summer is easier than others, it doesn't really make any sense. I don't see anything every day. No, I mean, like, I see everybody the same kind of time, and some, it's like, maybe that is, and some. I think so. Well, I mean, that's really something your mind does, it makes you think that. It's not really true, right? It could have been named anything. We could have been named Judy or Rosalind or. Hmm? Right, but you said people do look like, some people look like, I don't know. Well, yes, I do. You knew Jacques Gabor was? She looked like Jacques.
equal to the side of the triangle. Right, so that'd be like the side of the angles. That's the triangles, right?
Homework again, sure. All right, has everybody at least gotten through the first column, first two columns? Okay,
The sine and cosine of the zero, the
yeah,
degrees to 60 degrees?
yeah. In the name of getting us out of here on time, what I'm going to do, I'll start to go over this, and you might want to complete this, if only for practice. Might come in handy to be able to do this, you know, on homework or quizzes and tests. Okay, anyone want to tell me what the sine of 0 is?
0.
0, okay, and the cosine?
1.
Okay, good. 30 degrees, which maybe I should have marked it this way, is pi over 6. I think we just talked about that. So the sine of 30 degrees is, it would be the square root of 3 over 2 if it was. Is that right?
No, it was 1/2.
1/2.
Yeah, it's 1/2 of 2.
So, again, I'm not going to go through the whole derivation, but 30 degrees, it's kind of the smaller angle of the 30, 60, 90. So if this is 1, this is a half, the square root of 3 over 2, so the sine is the opposite over the hypotenuse, so it's a half. But then we know the cosine has to be square root of 3 over 2. Let's jump to 60 because it'll be easier to do it now. 60 is pi over 3, and its sine has to be the opposite of these two, right? So square root of 3 over 2, 1/2, and 45 degrees is pi over 4. And what did we decide the sines and cosines were? 1 over the square root of 2 and 1 over the square root of 2. Okay, now, the rest of this, if you remember the earlier part of the lecture, is really easy. Well, maybe not this. 90 degrees, the sines and cosines are going to switch, right? Sine will be 1, cosine will be 0. 120, well, if you look at the way these things are aligned, 120 is, the 30 degrees is the reference angle for 120. So we know the sines and cosines are the same absolute value. Now we just have to figure out which of these is positive and which is negative. Does anyone remember?
Yes.
The second quadrant,
All the signs.
sine is
Cosine plus.
plus, and the cosine is
Minus.
minus.
Wait,
That makes the rest of this easy. 1 square root of 2 minus 1 over the square root of 2, square root of 3 over 2 minus the half.
this,
Yeah?
the sine of 120 is 1/2 and, am I doing that wrong?
The reference angle is 60.
I'm sorry? Wait.
Yeah.
Amra, do you have a question?
Yeah, shouldn't it be the other way around? Shouldn't it be the sine is 1/2 and the cosine is negative? I mean, the sine is root 3 over 2 and the cosine is negative 1/2.
Okay. It's always possible that I will make a mistake. Let's take a look. So, 120 degrees, right?
You got the sine is
Right.
root 3 over 2.
So that's 120 degrees. Reference angle is 60 degrees.
So shouldn't the sine...
So this should be switched.
So
Yeah.
the cosine is the adjacent over the hypotenuse, so that's 1/2. The sine is the opposite over the hypotenuse, so that's square root of 3 over 2. So all I really need to do here is figure out which of these is negative. Well, obviously, the x coordinate here is negative. Is that what I had? No. There you go. Okay. Easily fixed. Okay.
But the...
No, it's the cosine. I just had it right. Oh. Okay, shame on me. All right. mathematics, one has to have a clear head, right? Otherwise, people can talk into anything.
It's another.
Yeah, it's not the sign, it's
Oh,
the
you-
value. Like, it's the value, it's not positive negative issue.
Oh! Yes. See, we have two people smarter than one professor. Okay, good. Now you can, wait, hold on. I got one more minute. Wait. So there's a homework assignment, of course.
What about